Hello and welcome to the course of Introduction to Computer Architecture. This is going to be a long course, as in around 15 to 20 hours of video, so it's going to be very comprehensive. We'll start with Introduction to Computer Architecture, fundamentals of computer design, pipelining, branches and limits to pipelining, exploiting instruction level parallelism. We'll talk about memory, caches, multi-core, multi-threading, vectors, SAMD, GPUs, and then we'll go into multiple SoC designs and understand, based upon the case studies, how basically you use computer architecture in real life. Okay, so let's get started. As in the first question to be, we'll start with what actually is computer architecture, why is it important. We'll talk about computer architecture arena and some aspects of design goals, historically how the computer architecture has been developed, what is the performance of computer architecture. We'll talk about future trends with multi-core processors, some system on chips, and beyond that. Okay, so to introduce, right, the modern microprocessor, which is basically is the engine behind all the technology in this world, how we communicate, how we work, automatic car driving cars, your social media. The modern microprocessor is often the engine behind that. It enables multiple trillion-dollar businesses and markets like e-commerce, finance, social media. Over the years, as in since the first transistor was built in last century, we have been very rapidly in both increasing the performance and we have been reducing the cost in computing. So that you see that because of this exponential growth in performance, reduction in cost. You will see large Google data center, which employs multiple servers, or microprocessors, Apple Apple CPUs, which basically consist of billions of transistors. Over the years, power requirements have also steadily reduced. It has created new markets related to Internet of Things. So you have basically an Internet of Thing device measuring the water level of a dam, or a lot of sensors in your automatic car, which are all Internet of Thing devices, your Alexa devices, your Google Home devices. All this all have also basically improved because of increasing performance, reducing cost, reduced in power requirements, and all those goes into how you design your computer, how you design architect your design. It's all dependent upon that. So it's a massive topic. It impacts each and every aspect of VLSI design, and it's really important for VLSI engineers as they grow up in their career to understand computer architecture. Okay, so the modern computer is less than 100 years of old. First, actually, computers were electromechanical. These were wall-based machines, something like this, where you will have, as in these were produced in 1930s and 1940s. These are before first transistor was built. Today's machines, of course, are orders of magnitude faster, lower power, more reliable, and cheaper. Okay, so this has developed after the development of first transistors. It started to develop actually exponentially, and the improvement in performance and speed and reliability actually increased exponentially. So for compute, let's go back to, like, we talked about at a high level. Let's understand for computer architecture, it's important to understand the levels of abstractions we deal with. Okay, so the first level of abstraction is what we call as architecture. Okay, architecture is a set of specification that allows developers to write both software, firmware, and hardware. This typically basically includes the instructions set. It has basically understanding of exceptions, memory models that your OS is actually going to rely on. This term architecture is interchangeably uh, uh, basically interchangeable with instruction set. Okay, instruction set. Now, so basically, what we are defining here at the architecture level, and when we're talking about abstraction at architecture level, is basically what is going to be a hardware software interface. It's kind of a contract between your software and hardware in terms, so that basically software can work independently based upon understanding that there will be a certain set of instructions that which will be followed. So this is the highest level of abstraction, and basically you are kind of defining a hardware and software level of interface. Then slightly lower level of abstraction is what is known as micro architecture. Okay, so basically, right, like architecture is defining instruction set. It does not define actually how your processor is being built. You can have two processors implementing the same architecture, same instruction set, but they can have lower level details which are different. So different micro architecture. They were built in different ways. Okay. One way to look at this, imagine architecture is basically you have two cars. Both cars basically take you from place A to place B, but they can both are cars. Okay, both work on, like, you have a clutch, you have a gear. If it's a stick shift, you have basically to turn left or right. You have a steering, but both can be implemented completely differently, and that you can understand once you go to lower level details or lower level of abstraction. So that is something of an analogy for your computer architecture. Micro architecture is something basically at a more detailed level of abstraction, lower level of abstraction than architecture. Architecture is a hardware software interface, but micro architecture will tell you how the processor is built. And now, given the same architecture, there can be different micro architectures, and they may manage different trade-offs differently. Typical trade-offs are your performance, cost, power, consumption, complexity. There can be other trade-offs: security, reliability, or etc. Right? So for the same architecture, once you go to the detail, different micro architectures can be constructed. Once you go to further lower in abstraction level, it's the real hardware or real hardware which you are implementing, which is basically what technology you are building on. It's the real hardware. What is the physical structure? What are the gates in the design? What is the packaging in the design? So basically, different parameters, different sub technologies can be detected. Different technology nodes, different frequencies, and that goes closer to hardware, how you're implementing it. So when you talk about computer architecture, these are different level of abstraction. One is architecture, which is basically kind of your hardware software interface, and micro architecture, closer to hardware, but still at a higher level. And then basically your real hardware or implementation details. So these are the different levels of abstraction in which people talk about computer architecture, or as I would say, your system architecture. Okay. Now, what are architecture specifications? We start with highest level of abstraction. That is what is architectural specification. And as I mentioned, right, it's kind of a contract. It's basically, this allows your developers to write software and firmware. So it's kind of basically a contract or kind of specification between hardware and software. Okay. Given the same architecture, many different compatible processors may be implemented. Maybe they differ in technology node, they differ in power requirements, consumption, cost, etc. Okay. So when a software is written for a given architecture specification, it will work for, basically it's portable between different architectures, where the micro architectures may be different mostly. IBM System 360 was the first family of compatible processors. It's basically initially consisted of 6 compatible computers. So 6 compatible micro architectures computers were there. And they differed in performance. The performance of the fastest machine was 50 times faster than the slowest. Basically, previous to that, so this is something IBM moved to. Previous to that, IBM started with architectures which were not compatible with each other. And you see, right, as in when you use this, method, you can actually be compatible, and basically you can port software from one micro architecture to another, as long as you stay consistent in your architecture specification, which is kind of a contract between the hardware and the software. So to explain more in detail, computer architecture is not just basically defining the instruction set or high level architecture. When the person who is defining the architecture must understand multiple aspects of the design, all level of the designs, and figure out what are the multiple options which are available both at microarchitecture level and at the software level to deliver the requirements. These requirements can be performance requirements, security requirements, power requirements. So it's both science and art. And as one famous quote from Markell in University of Wisconsin, that computer architecture is the science and art of selecting and interconnecting hardware components to create computers that meet functional performance and cost goals. So it's somewhere between our science and an art, and you kind of have to figure out what are various permutation and combinations possible between multiple hardware components at software level, at also basically at microarchitecture levels to meet your performance, functional goals, cost goals, nowadays security reliability goals as well. So computer architect or chip architect is concerned with how best to exploit not only software and hardware configurations, also to fabrication technology to meet the marketplace demand. Basically, example, right? How best we use 5 billion gate transistor and a power budget of 2 watts to design the chip at the heart of a mobile phone. So at the heart of the mobile phone, Apple would be thinking, okay, I only have 2 watts of power and I have 5 billion transistor. How can I use this 5 billion transistor to best design the best chip which works for this mobile phone, which does your face detection, faster internet access, everything, right? So computer architecture basically builds on a few simple concepts, and it's challenging, as you can see, right? As in you're cramming more and more devices, the performance requirements are always bigger, our requirements are always, as in you always want less time to charge. So basically it's based upon simple concept, but it's one of the most challenging aspect of your hardware design and architecture design, and we should constantly seek new solutions. What constitute the best designs? It depends on a use case. Maybe let's say you're designing a server, you always have access to power, so that your use case is different. You're designing a cell phone, you're relying on a battery, so your use case is different. And based upon your use case, the trade-off may be different. Maybe server which is Facebook is using for its basically social engine may have different cost requirement than versus maybe a low-end cell phone which may have a different cost requirement because the consumer is different. So the use case, how technology evolves over time depends, changes how what trade-offs are for that particular applications. So earlier we talked about three level of abstraction when designing a computer architecture or a processor. We talked about architecture, which is kind of a contract between software and hardware. Microarchitecture, a little bit higher level, little bit less abstraction level, where you go into more details how hardware is implemented and actual hardware, your technology node, what are the chips, what are the gates, all that. Okay. Now basically, we can extend these factors beyond processor itself. You can have fabrication technology. What is your target market? What are the applications? What are the programming languages and compilers it's going to work? Each level of this imposes different requirements and constraints, which can change over time. And basically, there is also economics. There is also what are the costs which are involved to design hardware and software. These are also consideration when it is chip architecture also has. Plus, as in you also need to look forward and not for design for yesterday's technology. For example, you are designing for a automatic driving car where you want to drive 5 years later. So you have to think about that as well. So design decisions is even though based upon simple concepts, it's basically complex decisions. You have to carefully think, do a lot of experimentation. There are multiple tools available to do these experimentation, and then basically justify why this architecture works. Also, once you select an architecture, it you should work for a long amount of time across multiple microarchitectures, because software cost can be huge as well. So it's basically all these decisions have to be carefully justified through experimentation.